All right, so this is the beginning of a new chapter. The first fundamental notion and the first chapter in number theory are on divisibility in prime numbers. And the second is on congruence classes or congruences. So we start with m, a positive integer. So m is called the modulus. And if a and b are integers such that m divides their difference, a minus b is divisible by m, then we say that a and b are congruent modulo m. So this is the fundamental definition. All right? You fix an integer m that's positive, the modulus, and we say that integers a and b, positive, negative, or zero, are congruent modulo m if m divides a minus b. And the notation for congruence is the following: a, 3 lines, congruent to b, mod m. So this is one of the key notions in number theory. And we say the opposite holds: a and b are incongruent, that just means not congruent, modulo m, if they're not congruent, modulo m, if a is not congruent to b, mod m. So for example, if you take m equal to 5, 17 is congruent to 12, mod 5, because 17 minus 12 is 5, which is divisible by 5. It's 5 times 1. 17 is congruent to minus 13, mod 5, because 17 minus minus 13 is 30, is 5 times 6. It's divisible by 5. Minus 12 is also congruent to 43 mod 5, because minus 12 minus 43 is minus 55, is 5 times minus 11. Minus 12 also also is congruent to 43 modulo 11, because minus 12 minus 43 is minus 55, is divisible by 11. It's 11 times minus 5. Just 1 second. Minus 12, what is it modulo 7? Well, It's not congruent. Minus 12 is not congruent to 43 mod 7 because minus 12 minus 43, which is minus 55, is not divisible by 7. Okay. So this is the definition of congruence. Any questions about that? This is really one of the most important notions in number theory. And let's look at some properties of congruence. So let me just repeat the definition. M is a positive integer. A congruent to B mod M if M divides A minus B. So this is a relation between integers. Given a pair of integers, they are or they are not congruent modulo M. And this relation has 3 properties we love to see. So properties of congruence modulo M. You can't talk about a congruence without referring to a specific integer, positive integer M, the modulus. So the first property is what is called reflexivity. A is congruent to A. So you fix your modulus M. A is congruent to A mod M for all A, Y, because A minus A is 0, and 0 is divisible by M. 0 is M times 0. Second, symmetry. Symmetry says if A is congruent to B mod M, then B is congruent to A mod M. And what is the proof of this statement? If A is congruent to B mod M, that means M divides A minus B. That means A minus B is M times Q for some integer Q. If you multiply by minus 1, B minus A is minus A minus B. So that's minus MQ. So that's M times minus Q. So B minus A is also a multiple of M. M divides B minus A. So B is congruent to A mod M. Okay. So this notion of congruence, this relation is reflective and symmetric, and it's also transitive. So the third property is transitivity. And what this means is if A is congruent to B mod M and B is congruent to C mod M, then A is congruent to C mod M. And what is the proof of this? Well, if A is congruent to B mod M, that means A minus B is some multiple of M. I'll say MX for some integer X. And if B is congruent to C mod M, then B minus C is M times Y for some integer Y. If I take these two equations and add, the b's cancel, I get a minus c is mx plus my, right? If I add the right-hand sides, I get a minus b plus b minus c, that's a minus c, and mx plus my, which they teach you in elementary school, is m times x plus y, which means a minus c is a multiple of m, so a is congruent to c mod m. So a relation that is reflexive, symmetric, and transitive is called an equivalence relation. That's just the definition. An equivalence relation is a relation that has these three properties. That is reflexive, symmetric, and transitive. And an equivalence relation on the integers divides the integers into sets which are equivalence classes. And when we have the relation of congruence, so for a fixed modulus, that means a fixed integer, m, the modulus is always positive. The congruence class of a modulo m, so this is the notion that I'm defining, is the set of all integers b such that b is congruent to a mod m, or a set of all integers. That's fine. All integers, maybe call it x. All integers x congruent to a mod m. So the simplest example of this you learn in elementary school when they tell you about even and odd integers. So suppose you let m equal to 2. So then what does it mean to say b minus b is congruent to a, or a is congruent to b mod 2 means 2 divides b minus a, which means b minus a is even, right? Divisible by 2, which means either a and b are both even, or a and b are both odd, right? The difference of two even numbers is even. The difference of two odd numbers is even. So 7 is congruent to 111 mod 2, because 7 minus 111, what is that? Minus 104. That's 2 times minus 52. It's an even number. And I mean, it's easy. 358 is congruent to minus 224 mod 2, because the difference, 358 minus 224, that's 358 plus 224. I don't have to even add it up because all I have to know is whether this is even or odd. And this is a sum of two even numbers. If you do add it up, you get what? 582, I think. In any case, it's even. And 39 is not congruent to 20 mod 2 because 39 minus 20 is 19, is not even. So a basic example of this idea of a congruence is just even and odd numbers. And those you know very well, so everything should be okay. And also in terms of terminology, a congruence class modulo M is also called a residue class modulo M. So these are just synonyms. Now, what is a very simple situation where you see a congruence? Let A be an integer, and you always fix your modulus M, some positive integer. If you divide A by M, you know that A is M times the quotient plus the remainder, where the remainder is between 0 and M minus 1. So you fix your modulus M. If you take the integer A and divide it by M, you always get a remainder between 0 and M minus 1. And A minus R is equal to M times Q. So A minus R is divisible by M. So A is congruent to R modulo M. So every integer, when you divide it by M, is congruent to its remainder mod M. And R is between 0 and M minus 1.
Professor,
Yes.
I'm sorry to interrupt you. There's a student that is waiting for you to be accepted to, he's in the waiting room.
I'm sorry.
There's a student in the waiting room waiting for you to be.
Oh, I just let them in. Thank you.
Okay.
Yeah. So what this says is that every integer is congruent modulo M to some number between 0 and M minus 1. Every integer A is congruent modulo M to some integer R, non-negative integer between 0 and M minus 1. Moreover, every integer is congruent to a unique integer in this range. So suppose R1 and R2 are integers in 0 up to M minus 1. Let A be an integer such that A, first of all, is congruent to R1 mod M, and A2 is congruent, and A is also, this is just my A, congruent to R2 mod M. Okay. So suppose some number A is congruent to R1 and R2, R1 and R2 in this set. So by symmetry, A congruent to R1 means R1 is congruent to A. By transitivity, R1 congruent to A mod M and A congruent to R2 mod M implies R1 is congruent to R2 mod M. So we have R1, R2 integers between 0 and m minus 1, and R1 congruent to R2 mod M. So therefore, R1 minus R2 is divisible by M, right? Two numbers are congruent modulo M if M divides them. So the absolute value of R1 minus R2 is M times the absolute value of Q. And R1 and R2, they're integers between 0 and m minus 1. That is, on the number line, here's 0, here's m minus 1. R1 is one of those numbers, R2 is another of those numbers. The difference between them in absolute value is at most m minus 1. If Q is not 0, then the absolute value of Q is at least 1, and we get the following: m minus 1 less than or equal to absolute value of R1 minus R2, m times the absolute value of Q, but Q is greater than 1. But that's absurd, because you can't have a number which is at the same time less than m, greater than m, Q times 1, m times 1. You can't have a number which at the same time is at least m and smaller than m. So therefore, Q equals 0 and R1 equals R2. So recall, what were R1 and R2? We had a number A congruent to R1 mod M, and number R2 where A was congruent to R2 mod M, and R1 and R2 were between 0 and m minus 1, and that means that R1 has to equal R2. That's what we just proved. So we proved the following result: every integer is congruent modulo M to exactly one integer in the set 0, 1, 2, up to m minus 1. Oops. With that, and so let's just look at some examples of that. If we take m equal 2, the set of integers 0, 1 up to m minus 1, well, if m is 2, m minus 1 is 1. This is just 0 and 1. So this says that every integer A satisfies either A congruent to 0 mod 2 or A congruent to 1 mod 2. And what do we call these numbers? The even integers and the odd integers. So the congruence class of 0 mod 2 is the set of all even integers. And the congruence class of 1 mod 2 is the set of odd integers. Suppose we take m equals 3. So the numbers from 0 to m minus 1 are 0, 1, and 2. So you take a number a, divide it by 3, you get a quotient and a remainder, and the remainder is 0, 1, or 2, and a is congruent to r mod 3. So the integers are mod 3 are divided up into 3 different congruence classes. So for example, r equals 0. The congruence class of 0 modulo 3, it's all integers which leave a remainder of 0 when you divide by 3. Namely, the set of all multiples of 3, 3, 6, 9, 12, 15, and so forth. And the odd multiples of 3, of course. That's the congruence class of 0. And if you look at this on the number line, it's a sort of this infinite progression of integers, always differing by 3. That's the congruence class of 0. Any questions about this? This is a very simple notion. I mean, in principle, you could teach this to kids in elementary school as soon as you teach them long division, because we're not doing anything else, but it's a somewhat more sophisticated way of looking at it. Well, mod 3, there are 3 congruence classes. This is the congruence class of 0. What is the congruence class of 1? So the congruence class of 1 modulo 3 is the set of all integers a, such that a is congruent to 1 mod 3. So that's the same as the set of all integers a, such that a minus 1 is divisible by 3, 3 times q. So it's all integers of the form a equal 3q plus 1. For any integer q. What is this set of integers? When q is 0, 3 times 0 plus 1 is 1. When q is 1, 3 plus 1 is 4. When q is 2, 3 times 2 plus 1 is 7. When q is 3, 9 plus 1 is 10. When q is 4, 12 plus 1 is 13, and so forth. This is just this progression, 1, 4, they go up by 3. What about when q is minus 1? You get minus 3 plus 1, that's minus 2. When q is minus 2, you have minus 6 plus 1 is minus 5. When q is 3, you have minus 9 plus 1 is minus 8. When q is 4, you have minus 12 plus 1 is minus 11, and so forth. Again, these are going down by 3. And again, if you look at this on the number line, you have 1, 4, 7, 10, 13, going up by 3, and going down by 3. Just this infinite progression differing by 3 on the number line, but not 0, 3, 6, it's 1, 4, 7. That's the congruence class of 1. And if R is 2, the congruence class of 2 modulo 3, this is a set of all A congruent to 2 mod 3. That means all numbers A where A minus 2 is 3 times Q for some Q, or all numbers A, bring the 2 to the other side, of the form 3Q plus 2. So when Q is 0, 0 plus 2 is 2. When Q is 1, 3 plus 2 is 5. When Q is 3, 9 plus 2, sorry, when Q is 2, 6 plus 2 is 8. When Q is 3, 9 plus 2 is 11. These are going up by 3. When Q is minus 1, minus 3 plus 2 is minus 1. Q is negative 2, minus 6 plus 2 is minus 4. Again, these are decreasing by 2. Right? And on the number line, you have 2, 5, 8, 11, minus 1, minus 4, and so forth. Right? This is the congruence class of 2. And if you want to look at all the integers, so 1, 2, 3, 4, 5, 6, 7, 8, 9, minus 1, minus 2, minus 3, minus 4, minus 5, minus 6, minus 7, minus 8. Okay, so let's write in red all integers A congruent to 0 mod 3. That's 0, 3, 6, 9, minus 3, minus 6, and so on. Those numbers are congruent to 0 mod 3. What are the numbers that are congruent to 1 mod 3? I'll write them in green. So 1, 4, 7, minus 2, minus 6, minus 8. What about the numbers that are congruent to 2 mod 3? I'll write them in blue. 2, 5, 8, minus 1, minus 4, minus 7. You see these intertwine. So these are the numbers that are congruent to 2 mod 3. These are the numbers that are congruent to 1 mod 3. Those are the numbers that are congruent to 0 mod 3. You have this very pretty intertwining of red, green, blue. Red, green, blue, red, green, blue, red, green, blue, red, green, blue, red, green, blue. It's very pretty. It's a very visual way to see these congruences. Okay. And remember, we showed a moment ago the following statement. every integer is congruent modulo m to exactly one integer between 0 and m minus 1. And we call that integer is the least or smallest non-negative residue of A modulo M. So a simple problem would be, for example, find the least non-negative residue of, I don't know, 39 modulo 7. So modulo 7, you're going to have a number between 0 and 6 that's congruent to 39 mod 7. How do you find it? Divide. If you divide 7 into 39, that goes in 5 times and leaves a remainder of 4. In other words, 39 is 7 times 5 plus 4. So 39 is congruent to 4 mod 7, and the least non-negative residue is 4. So to say that 4 is the least non-negative residue of 39 minus 7 modulo 7 means 39 is congruent to 4 mod 7, and 4 is the unique integer between 0 and 6 with that property. Right. Any questions about this? All right. So here are 2 problems for you to do right now. Find the least non-negative residue of minus 18 modulo 7, and find the least non-negative residue of 128 modulo 13. So problem 1 and problem 2. So spend a minute. This means find an integer between 0 and 6. There will be one and only one such integer, congruent to minus 18 mod 7. And find the unique integer between 0 and 12 that's congruent to 128 modulo 13. Okay. Can anyone give me the answer to the first problem? What is the smallest or the least non-negative residue of minus 18 modulo 7?
I believe it's 3.
Sorry?
I don't know why you're still getting my game.
I believe it's 3.
3. Okay, let's check. So
I don't like cheating.
So negative 18
Why
is equal to 7 times negative 3.
minus
plus
18 minus 3 is minus 21 is 7 times minus 3. So that works. Minus 18 is congruent to 3
Maybe 100.
mod 7.
100 again? I don't want 100.
Okay. Good.
Professor, sorry, just a quick question. So I know it went in with a -3, but you just make it up the sign is 3?
No. So this
Positive or-
is A is minus 18 and B is plus 3. So when you look at A minus B, in this case, that's equal to minus 18 minus 3,
Okay,
right? Which is minus 21.
yeah.
Another way to say that is, well, it's the same thing. This is exactly the division algorithm. If you take minus 18 and you divide it by 7, that's minus 3 times 7 plus 3. I mean, the fact that you have 2 3s there is just a coincidence. And what about 128 mod 13? What is the least non-negative residue of 128 mod 13?
I think 9.
Well, let's see. If you take 128 minus 9, that's 119. And if you divide 13 into 119, seven threes are 21, 9. No, if you divide it 8 times, 4, 8, 13 into 119, 8 threes
I'm
are,
sorry, Professor, that is wrong because I put mod 17, not 13.
right, okay. So what, we still need the answer to the problem, right? The least non-negative residue of 128 modulo 13.
11.
If you divide 13 into 128, that goes 8 threes are 24. Well, maybe it goes 9 times. 9 threes are 27. It leaves a remainder of 11. So 128, when you divide it by 13, has a quotient of 9 and a remainder of 11. So 128 is congruent to 11 modulo 13. This 11 is between 0 and 12. It has to be 1 less than the modulus at most. And the difference is divisible by 13. So that's the answer. Any questions about this? These are So in computing congruences, there's some arithmetic properties that hold that are very useful. So suppose, so we fix the modulus. You always fix a modulus m. Suppose A1 is congruent to A2 mod m, and B1, you have another congruence mod m, B1 is congruent to B2 mod m. So this means that A1 minus A2 is m times some number x, and this means that B1 minus B2 is m times some number y. So A1 is A2 plus mx, and B1 is B2 plus my, right? So if A1 is congruent to A2, A1 minus A2 is divisible by m, so A1 is A2 plus mx for some integer x, and similarly, B1 is B2 plus my for some integer y. If I add these two equations, what do I get? I get A1 plus B1 is A2 plus mx plus B2 plus my, which if I rearrange this is A2 plus B2 plus m, x plus my, that's m times x plus y. But that says that A1 plus B1 is congruent to A2 plus B2 modulo m, because the difference of these two numbers is divisible by m. So A1 plus B1 is congruent to A2 plus B2 mod m. In other words, if you have two congruences modulo m, and you add them, you get another congruence modulo m. So that's very nice.
Professor, stupid question. We're taking mod m to be the same value, correct?
M not, yes, everything is for a fixed modulus.
Okay,
Fixed
gotcha.
modulus m. If you have different moduli, this is nothing, doesn't
Okay.
work. Now, what about multiplication? A1 times B1. A1 times B1. A1 is A2 plus mx, and B1 is B2 plus my. So we just distribute across, we get A2 B2 plus A2 my plus mx B2 plus mx my. Right? That's all these four terms. This is A1 B1 equals A2 B2. And from each of these terms, I can factor out an m. So plus m times A2y plus xb2 plus x my. In any case, this is an integer. So A1 B1 minus A2 B2 is a multiple of m. So A1 B1 is congruent to A2 B2 mod m. So what this tells us is, with respect to a fixed modulus m, you can add congruences and you can multiply them. Right? That's very, 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 very interesting. Now, I want to put this in a somewhat different setting, which in mathematics is very important. Remember, we defined the congruence class of A modulo M. The congruence class of an integer A modulo M is a set of integers. It's all integers. I'll just write it, I'll call it maybe A prime. All integers A prime, such that A prime is congruent to A modulo M. And the notation for this is A plus M Z. Remember, this kind of bold-faced Z means the set of all integers. And the reason is, what are the numbers that are congruent to A mod M? You have A plus M, A plus 2M, A plus 3M, and so on forever, and A minus M, A minus 2M, A minus 3M, and so on in the negative direction forever. That is the congruence class of A modulo M. And if we take the congruence classes 0 plus MZ, which we usually just write, that's a congruence class of 0. We usually just write that as MZ. That's going to be, this is A equals 0. So this is just a set of all multiples of M, 0, M, 2M, 3M, minus M, minus 2M, and so forth. That's the congruence class of 0 mod M. If I take MZ, the congruence class of 1 plus MZ, the congruence class of 2 plus MZ, and so forth, up to the congruence class of M minus 1 plus MZ, we showed that every integer is congruent to exactly one of the numbers 0, 1, 2, 3 up to M minus 1. So if I take the union of all of these congruence classes, that's all the integers. And we prove that every integer is congruent to one and only one of these. So these congruence classes are disjoint. That is, A plus MZ intersect B plus MZ is this. This means the empty set, the set with nothing in it. If A is not congruent to B modulo M. So when you fix a modulus M, you've partitioned the set of all integers into these M sets, which are pairwise disjoint. They have no elements in common, and together they give you all the numbers. And we define, this is our notation, Z, this is read as Z mod MZ. This is the set of all the congruence classes mod M. So this is the congruence classes A plus MZ, where A is in some integer between 0 and M minus 1. So now this is something you really need to spend a lot of time at home thinking about. So the integers form an infinite set. We'll take M equal 2. The integers are an infinite set, but you can divide it into two subsets, the even numbers and the odd numbers, right? So Z mod 2Z consists of 0 plus 2Z and 1 plus 2Z, those two sets. All we're saying is these are the evens and these are the odds. So I can take the integers and I define it as two sets, the even numbers, the set of even numbers, and the set of odd numbers. And you remember from, I don't know, kindergarten even maybe, I don't know. If you have an even number plus an even number, that's an even number. And if you had an odd number plus an odd number, that's an even number. And if you take an even number plus an odd number, that's an odd number. And an odd number plus an even number is again an odd number. So you could actually write a kind of addition table. even, this is for plus, even, odd, even, odd. Even plus even is even. Even plus odd is odd. Odd plus even is odd, and odd plus odd is even. Right? Now, remember that the congruence class of 0, these are the evens. The congruence class of 1, these are the odds. So I could rewrite this table as follows. Instead of the set of even numbers is 0 plus 2z. Set of odd numbers is 1 plus 2z. Let me just forget the 2z's. 0 plus 0 is 0. 0 plus 1 is 1. Remember, even, odd, odd, even. Odd, even means 1, 0. This is another way of writing the addition rule for even and odd numbers. Of course, this is really the congruence class. Though we would abbreviate it just like 0. This is the addition table. So the simplest baby facts about adding even and odd numbers, that's an example of adding congruence classes modulo 2. So let me define addition of congruence classes. If I take always modulo m, the modulus never changes. So a plus mz plus b plus mz. I claim I can define that to be just the congruence class of a plus b plus mz. And now, the reason why there's something you need to prove that this definition makes sense is the following. Suppose I take, let's say, m equal to 7. I mean, m equal to 5. So I take the congruence class of 3 plus 5z and the congruence class of, I don't know, 11 plus 5z. According to this rule, this is the congruence class of 14 plus 5z. Let me take another example. Suppose I take the congruence class of 18 plus 5z plus minus 4 plus, oh, that's a bad example, plus 26 plus 5z. By the same rule, this is going to be 18 plus 26, that's 44 plus 5z. All right. Well, what is the problem? The problem is the congruence class 3 plus 5z is equal to the congruence class of 18 plus 5z. Because everything congruent, 3 is congruent to 18 mod 5. So any number congruent to 3 modulo 5 is congruent to 18 mod 5. And similarly, 11 plus 5z equals 26 plus 5z. These are 11 and 26 are different numbers, but these two congruence classes are the same. Because 26 minus 11 is 15 divisible by 5. 11 is congruent to 26 mod 5. So if these are equal and these are equal, then these have to be equal. And in fact, they are. 14 is congruent to 44 mod 5. Of course, the difference is minus 30 is divisible by 5. So 14 plus 5z is equal to 44 plus 5z. But we have to prove that this is not just a lucky fact. It's always true that this definition makes sense. So this is a somewhat subtle point, and it takes a fair amount of time and work and thinking to understand this, but this is going to be the point. So we have that A1 plus MZ, that congruence class equals A2 plus MZ, if and only if A1 is congruent to A2 mod M. And B1 plus MZ equals B2 plus MZ, if and only if B1 is congruent to B2 mod M. But in this case, you can add congruences. A1 plus B1 is congruent to A2 plus B2 mod M. We proved you can add congruences. So A1 plus B1 plus MZ, that congruence class does equal A2 plus B2 plus MZ. So if we want to define A1 plus MZ plus B1 plus MZ to be equal to A1 plus B1 plus MZ, and A2 plus MZ plus B2 plus MZ equals A2 plus B2 plus MZ. It doesn't matter which representative of the congruence class you pick, A1 or A2, or in this case, B1 or B2. These are equal. So this is a well-defined notion. So this says that addition of congruence classes is well defined. So we can define addition of congruence classes in a coherent way. And you can also multiply congruence classes. If you take A plus MZ and B plus MZ, you can define the product to be AB plus MZ. And this also is well defined. And in fact, all of the nice properties of addition and multiplication of integers carry over to congruence classes. So I'm going to give two definitions, and then I think that's a lot for today. It's already a lot. So suppose we have a set X with a binary operation, like this could be the integers, and the binary operation could be addition. That is, given two elements in the set, you can get a third element, like X1 and X2, there's a way to add them. That would be a binary operation. Or multiplication, when you can do that, X1 times X2, that's another binary operation. So we say a set X with a binary, and since I don't know, I don't want to specify either addition or multiplication, it could be one or the other or something else. I'm just going to use a symbol like an asterisk. This is going to denote like addition or multiplication, right? So for any two elements in the set X, you can, I'll just say multiply them. So a set X with the binary operation is called a group if it satisfies the following properties. First, this binary operation is associative. That means that X time or A times B times C is A times B times C. So for addition, this just means that A plus B plus C is A plus B plus C. For multiplication, if you're using multiplicative notation, that would mean AB times C is A times BC. That's what associative means. Second, there exists an identity element E, and the identity has the property that E times A or A times E is equal to A for all elements A in the set X. So for addition of integers, we take E to be 0, and we know that A plus 0 and 0 plus A is always equal to A. And for multiplication of integers, the identity element would be 1. A times 1 and 1 times A is always equal to A. Third, every element A in X has an inverse B, what that means in X, such that A times B and B times A are both equal to the identity. So for addition, where the identity is 0, the inverse is minus A, right? You know that A plus minus A and minus A plus A equals 0. And then let's say the rational numbers, the non-zero rational numbers, where the identity is 1, B might be 1 over A, because A times 1 over A and 1 over A times A is equal to 1. This is in, say, X is the set of non-zero rational numbers. So a set X that has this a binary operation with these three properties is called a group, and X is an abelian group or a commutative group. These mean the same thing. If the order in which you do the binary operation doesn't matter, A times B is B times A. So for addition of integers, you know A plus B equals B plus A. And for multiplication of non-zero rational numbers, A times B is B times A. So some examples of an abelian group are the integers under addition and Q star. This means the non-zero rational numbers. And from what I just proved, Z mod MZ is also an abelian group under addition. Of course, you can add congruence classes. And so that's what a group or an abelian group is. And a ring is an additive abelian group. So it's an abelian group called R. A set R is a ring if, first of all, there's an operation of addition such that R is an additive abelian group with respect to addition, and R also has a multiplication operation that satisfies the following properties. First of all, the multiplication is associative. AB times C is A times BC. An identity element exists. To call it, say, 1. So A times 1 and 1 times A is equal to A for all A. And third, we have the distributive laws. So A times B plus C is AB plus AC. And A plus B times C is AC plus BC. So if you have an additive abelian group that also has a multiplication, if the multiplication is associative, there's an identity element, and you have distributivity, then it's called a ring. And R is a commutative ring if the multiplication is commutative, that is A times B is B times A for all A and B in the ring. And the two most important examples, or three or more, says first of all, Z, the integers. You can add and multiply them, and they have all these properties. The rational numbers. They don't form a group under multiplication, but they do form a group under addition, and multiplication satisfies these properties. And what is for us now the most important example, congruence classes modulo M. This is a finite commutative ring because there are only a finite number of congruence classes mod M. But you can add and multiply them, and they have all these beautiful properties. Okay. All right, wow. So we just covered, I think, a lot of material. And it's really important to spend a lot of time understanding this section. Because there's a lot of mathematics embedded in this. Okay. Any questions that I should answer right now?
Real quick, Professor, when is your next office hours?
So I will have office hours. I had to set up a couple of office hours for specifically for a different class, but we'll have office hours here, I think, Thursday, tomorrow. Well, definitely on Friday afternoon, and Thursday, when on Thursday can we do it? Maybe sometime on Thursday morning, and it can be almost any time. So if anyone wants an office hour on Thursday morning, unmute yourself or go to chat and say what time you would prefer. And I'll pick whatever is the most popular time, right? So for an office hour tomorrow morning, just pick a time. 9 o'clock is fine for me. Just up to you. So I have 2 votes for 9, 3 votes for 9. No, okay. So let's say 9 o'clock tomorrow morning, and I will post it on Blackboard shortly, so everybody knows.
Professor,
Yes.
in one of the homeworks, you are asking to construct a multiplication table for a ring. So what do you mean about that?
Oh, okay. So let's take the simplest case. M equals 2. So Z mod 2Z only consists of 2 congruence classes, 0 plus 2z and 1 plus 2z. And we can add and multiply the congruence classes. So the addition table, let me just write 0 and 1 instead of the plus. That just means 0 plus 2z and 1 plus 2z. When you add, this is the addition table, right? And when you multiply, even times even is even. Even times odd is even, and odd times odd is odd. This is the multiplication table. Right? What this means,
Okay. Mhm.
if you had z mod, if you take m equal 3, z mod 3z, you have 3 congruence classes. Zero, 1, 2, 0, 1, 2. When you add, 0 plus 0 is 0, 0 plus 1 is 1, 0 plus 2 is 2, 1 plus 0 is 1, 1 plus 1 is 2, 1 plus 2 is 3, which is the same as 0 mod 3. 2 plus 0 is 2, 2 plus 1 is 3, which is the same as 0. 2 plus 2 is 4, which is the same as 1. So this is the addition table. And when you're multiplying congruence classes, 0 times 0, 1 or 2 is 0. So these are all 0. 1 times 1 is 1. 1 times 2 is 2. 2 times 1 is 2. 2 times 2 is 4, which is the same as 1. So this is the multiplication table.
Got it. Thank you, Professor.
Okay. Okay, all right. So I'll be back 9 o'clock tomorrow morning for anyone who wants to join an office hour and ask questions. Okay. Okay, that's it for this morning. Bye all.
Okay, Professor, have a good day.
Have a good day, Professor. Thank you.